The fundamental theorem of calculus opened a whole new world to mathematicians and scientists in the 17th century. Solutions to problems that had been nagging scientists and mathematicians were now easily found. Hi, my name is Tom Atwater, and that's what today's lesson is going to cover. Let's start with the fundamental theorem of calculus, part 1. If f is a continuous function on the closed interval a comma b, then the function capital F of x equals the integral of f of t dt evaluated from a to x has a derivative at every point x in the interval a to b, and the derivative with respect to x of capital F is equal to the derivative with respect to x of the integral from a to x of f of t dt, which will just equal f of x. Let's try this out with an example so that you can see how to use the fundamental theorem of calculus part 1. We want to find dy dx for the following functions. We have t cubed minus t quantity raised to the 5th power evaluated from 0 to x. And our second one that we're going to look at is the integral evaluated from 2 to 5x of the quantity square root of u squared plus 1 all divided by u du. Okay, so let's take a look at the first one and evaluate this one using the fundamental theorem. So what we're going to have then is that this is going to be simply equal to x cubed minus x raised to the power of 5. And that's what the fundamental theorem of calculus would tell us is our solution to the problem number 1. Now for problem number 2, we're going to have the solution, the square root of, this time 25x squared, which of course is what I get when I plug in 5x for u here. Then I have my plus 1, and that's all going to be over. Well, normally you would think I would put 5x down here, because then that's what I substitute in for u. But what you have to remember is that up above here, I would have to use the chain rule to differentiate that 5x, which was being squared, and that's where I got the 25x squared. But the derivative of 5x would leave me with 5 in the numerator. And so the 5 would cancel out the 5 with the 5x. So that is my final solution using the fundamental theorem of calculus. Well, now what I'd like to do is try a slightly different example. We want to construct a function of the form y equals the integral of f of t dt plus a constant evaluated from a to x that satisfies the given conditions. That dy dx is equal to the log of quantity sine x plus 5. And y is equal to 3 when x is equal to 2. So let's take a look at how we would use the fundamental theorem to construct that type of a function. So again, here's our problem. Dy dx is equal to log of the quantity sine x plus 5. So what we'll have is the integral from 2, which is the value of x where we are going to start, evaluated up to x of log of the quantity sine t plus 5 dt, plus the constant that we have to put in here, of course, is going to be y equals 3, since that's the value that we're looking for when x is equal to 2. And in other words, if we were to plug and evaluate this integral in for 2, which is the initial condition, then this part would drop out, leaving us with the plus 3, which would be the value for y, which is what we're interested in. Now, there's a second part to the fundamental theorem of calculus that is equally as important as part 1. So let's take a look at that right now. We have if f is continuous on the closed interval AB, and if capital F is any antiderivative of little f on that interval AB, then the integral of f of x dx evaluated from a to b is equal to capital F of b minus capital F of a. So this theorem, the second part, is equally important. So let's take a look at an example of where we would apply this. Evaluate each integral using part 2 of the fundamental theorem of calculus, and we have the problem number 1, the integral from 1/2 to 3 of the quantity 2 minus 1 over x dx. And for the second problem, we have the integral from 0 to pi over 3 of 2 secant squared x dx. So let's take a look at the first problem and apply the second part of the fundamental theorem of calculus. So we need to integrate 2 minus 1 over x dx. So the integral, of course, of 2 is going to be 2x. And the integral for 1 over x, remember, is the natural log of x. And we need to evaluate that all the way from the 1/2 to 3. So we need to plug in the 3, and that's going to give us 2 times x, which would be 6, minus the natural log of 3. And then we're going to have minus 2 times 1/2. So we're going to get 1 minus the log of 1/2. And when we evaluate that, we'll end up with 6 minus 1 is 5. And then minus, when we combine log 3 plus the log 1/2, we're going to get the log of 6. So that's the evaluation of the first integral, using the fact that you can evaluate it 3 and subtract it, evaluating it at 1/2. Let's take a look at the secant squared x dx problem. This one is going to be equal to, if you remember, secant squared, the integral of that is tangent of x. So we're going to have that this is equal to 2, because of the constant that we have out front here, and then it's going to be tan of x. And this one we need to evaluate starting at pi over 3, so 2 tan pi over 3 minus 2 tan of 0. Now the tangent of 0 is 0, so that all equals 0. The tangent of pi over 3, you remember, is the square root of 3. So our answer is 2 square roots of 3. So that gives us our answer for the second problem of the integral of 2 secant squared dx evaluated from 0 to pi over 3. We can use this same idea, this same procedure, to find areas. So let's take a look at how we can use this to find area. Find the total area of the region between the curve and the x-axis. And the curve we have is y equals x cubed minus 3x squared plus 2x, and we're going from 0 to 2 inclusive. Let's take a look at what that graph would be. And here we would have 1, and of course this is our 2, and we started at 0. And so what we're looking for is the area here added to the area here. And so what we're going to have to do here is split this up into 2 separate integrals. We're going to integrate from 0 to 1, and then we're going to integrate from 1 to 2. We will then add those 2 areas together to find the total area between them. Remembering that if I did not split those up, then the integral, when evaluated from 0 all the way to 2, we would have a positive and a negative that ends up canceling each other out, and we would get an area of 0. So we're splitting it up for that reason. So let's take a look at that now. And here's our original equation, our original function that we want to integrate. So what we'll have is we need to integrate x cubed minus 3x squared plus 2x dx. And as I said, we're going to go from 0 to 1 the first time. And so what we get here is this is equal to x to the 4th over 4. And that would be my x cubed minus x cubed, which gives me my 3x squared, and then plus x squared, which gives me my 2x. That's to be evaluated from 0 to 1. So we plug all of those in, and we'll get 1 to the power of 4 over 4 minus 1 cubed plus 1 squared minus, and then I think you can see this, each of these terms is going to be 0. All right, so all we're interested in is this part right here, and this minus 1 cubed, of course, is minus 1 plus another 1. Those add up to 0, so we have our answer of 1/4 for the integral from 0 to 1. But now what we need to do is integrate this from 1 to 2. So let's do that right now. What we have is the integral from 1 to 2 of the same exact problem, which means, of course, that we get the same formula for the integral. So x to the 4th over 4 minus x cubed plus x squared. And this time we're evaluating it from 1 to 2. Okay, so what we need to do is plug the 2 in for x as well as plug the 1 in for x. But while we're here, remember, we already evaluated this when it was 1. And so I'm going to shortcut that and say from the problem that the part of the problem we just did, that when we plug 1 in here, we're going to get 1/4. So let's just worry about the 2. The 2 would be 2 to the 4th over 4 minus 2 cubed plus 2 squared. All right, so here we have 2 to the 4th, which is 16 divided by 4, which is going to give us 4. So I have 4 minus 8 plus 4, which of course all adds to 0. I remember now that I have to substitute my 1 in there, but as we learned before, that was simply equal to 1/4. But remember, we subtract that off. So I still down here would have to have minus 1/4. So for this area, we get negative 1/4. So let's talk about that a little bit. We have the first area was positive 1/4, and that was above the x-axis. And now we're getting this negative 1/4, which indicates that it's below the axis. But since we are interested in that total area, we're going to essentially take the absolute value of the negative 1/4. We'll add the 1/4 from the first part that's above, plus the absolute value of this negative 1/4, which gives us positive 1/4. So our total area, of course, will be 1/2. Okay, well, now it's time for you to try a problem. And the problem I'd like you to do is this. Find the total area of the region between the curve and the x-axis, and the curve that you have is y equals 2 minus x, and I want it from 0 to 3 inclusive. Pause the video while you work on this problem. When you are finished, restart the video to check your solution. Welcome back. Let's find out how you did on this problem. The first thing I will do is take a look at the graph of y equals 2 minus x. And of course, it's this straight line, which we're evaluating, remember, from 0 to up to 3. And we have the same situation going on that we had before, which is that this part here being below the axis, we're going to break this up into the one integral from 0 to 2 and a second integral from 2 to 3. And we'll take care of the fact that this is below the axis, so we know that we'll get a negative answer there. This part, we'll get a positive answer. We don't need to worry about that. So let's forge ahead and take a look at integrating this. So we have y equals 2 minus x, and that's going to be the first integral from 0 to 2, and 2 minus x dx. That's going to be equal to, the integral of 2 is, of course, 2x. The integral of x is x squared over 2, and we want to evaluate that from 0 to 2. And so we substitute those in. We get 2 times 2, which is 4, minus 2 squared, which is 4 over 2, and then minus, and I'm just going to put 0 here because you should realize now that plugging 0 into those x's will give us 0. So we get an answer here of 4 minus 2 for 2. So the area of the first part is 2. Now we need to integrate the same formula from 2 up to 3. So the 2 minus x dx. So we already know what that's going to be from what we did earlier. So we'll have 2x minus x squared over 2 evaluated from 2 to 3. So we plug our 3 in there, and we get 2 times 3, which is 6, minus 3 squared over 2. And then we subtract, evaluating it at 2. But remember, we evaluated it at 2 over here. So we know that that is going to be equal to 2. So now it's a matter of simplifying the 6 minus 3 squared, which is 9. So 6 minus 9 halves minus 2. So the 6 and the minus 2 give us, of course, the 4. Then we have 4 minus the 9 halves, which, if you remember, or you can calculate, is 4 1/2. So what we have is that this is equal to minus 1/2. Minus 1/2. And so we have the same situation. We're going to take the absolute value of that, which changes it to positive 1/2. We add that to the area that we had from the first integral of 2. So our final total area is 2 1/2, which, yes, you could write that as 5/2. Either of those answers is acceptable, and that's the answer that hopefully you got. All right, great. So in this lesson, we looked at the fundamental theorem of calculus, parts 1 and parts 2. And we looked at how to evaluate integrals using that and how it would apply to finding the total area between a curve and the x-axis. Be sure to work the exercises that your teacher assigns, and we'll see you next time.